morning, everyone. It's really great to see so many friends and colleagues here. And I have to say that when the organizers asked me to give this talk, I was really delighted. But then I saw that Simon is giving the opening talk, and I knew it was going to be a difficult act to follow. Now I know that that's the case. So I did take some precautionary measures. So I'm going to talk about the application of system analytic tools to achieving sustainability in the future. And what I also wanted to just emphasize that I would like to do that in the context of the fact that not everybody benefits from the great progress that has been achieved during the last centuries. About 40% of the global population is excluded. And so we have to understand, and I hope that systems approaches is the most important way of understanding that, is how to provide adequate living on a safe planet from everybody. So that's basically what I would like to talk about, but since this meeting is celebrates Howard Dreyfus, let me just say a few words about Howard Dreyfus. As Pavel said in the beginning, Howard is the founding father of IASA, a great thinker, and he was deeply involved in organizing IASA. And there were a series of meetings in the 60s, and in particular in 1968, some of the really important decisions about IASA were made. For example, working language English, director from the United States, chair of the council from the Soviet Union. But then came the questions they couldn't resolve. What the institute should be really about? Is it about research and training, capacity building in current language? Is it about research of common problems, East-West, global, cybernetics? Should it be institute or a center? And there was quite lots of discussion about that, and then Howard, based on the book that he just published, I believe the title was something like Applied Statistics to Decision Theory, he proposed Institute of Applied Systems Analysis. Everybody was delighted, primarily because nobody really knew what it meant, and they thought the institute could start on the clean slate. So I think this is interesting because we heard this morning there were 75 definitions of systems analysis, and as it's being revived, as we heard from Simon, I think it's really important for us to have a collective understanding. Almost 50 years have passed. And so the discipline has increased, and I think this conference is a testimony to it. But if you want to know more about this, please look at the memoirs from Harvard, and also on the IASA website, there is really a great film where he talks about the history, systems analysis, IASA, and so on. Now, let me go back to my talk. I would like to start with this. I hope you can see it. It's a map of the world. What I'm showing you is carbon emissions as they emerged from the beginning of the Industrial Revolution. That started in United Kingdom. The spark went over to Europe. Now you can see it to United States. We are in the 1880s. This is the high days of coal. The world is industrializing now in the 1920s when oil started diffusing around the world, and you can see that fossil energy becomes really important. I would argue it is a proxy for the Industrial Revolution. So these 200 years of development have led to great progress, but as I said before, have excluded about 40% of the global population. And it's pretty much clear that these trends cannot continue. We have to find a new way of providing good living for everybody, and I think that requires a revolution. Perhaps one can call it a sustainability revolution. So my talk is a little bit wrapped about this idea. How do we transition from here to the next phase of the development of the human society? Now, Pavel has shown this. In September, the world community unanimously at UN adopted the 17 Sustainable Development Goals, something that I guess we should all memorize. I think they are really instrumental. I realize that they are, aspirational, but they need to be realized if we are going to achieve sustainable development. I will, of course, not read all of them, but let me just say I've highlighted it in red. You can see it's about poverty, eradication, hunger, improving health. Pavel mentioned 7, which is on energy. I'll talk a little bit about that. On 10, reducing inequality. 11, cities, because urbanization is one of the most powerful developments in our society. And then, of course, 17, which is about sustainable development. Now, they are behind the 17 goals, there are 169 targets. And Pavel already indicated that one of the goals, number 7, actually has quantitative targets that are rooted in science. The three targets are universal access to energy, and here at the Institute, colleagues are doing some really excellent work on how to provide universal access to the 3 billion people who are excluded. Another one is to improve the efficiency of the energy system, double it over the next, by the 2030, the rate of the improvement, and double the share of renewables, which is kind of a proxy for zero carbon. Now, this is very aspirational and ambitious, but it is rooted in science. It's based on the global energy assessment that was contributed by 500 people, that included 40 scenarios about how this transformation would be achieved and what one would need to do with an integrated assessment model. And I'm really delighted that became a goal number 7, because energy was excluded. I think we need a holistic picture, and it's important that the major drivers of our society are also included in our view of the future. Pavel has also shown this slide. Let me just walk you very quickly through it. The Sustainable Development Goals, in my view, since they're 17 with so many targets, they need science. We need to understand how they're related, and before the summit in New York, on behalf of ICSU, we published a paper in Nature commentary arguing that science must be at the heart of this process, not just a stakeholder, but at the heart of the process, to achieve synergies among the goals and avoid the goals blocking each other. So the systems point of view is absolutely essential, and I would argue that system science is absolutely necessary for achieving this transformation. Now, under the Sustainable Solutions Network, another initiative of Ban Ki-moon, Sustainable Energy for All is one of them that I just talked about. Another one is Sustainable Development Solutions Network. Pavel serves on the Leadership Council of that. Under that umbrella, we are initiating the World in 2050 study that was organized originally by IASA, Stockholm Resilience Center, and the Earth Institute of Columbia University. And the idea here is basically to understand how we can achieve the 17 goals, and then beyond that, allow or empower the transformation to a sustainable, safe future. 25 leading analytical groups have expressed interest in participating in this. We also at IASA, I'll just give you some examples. We have a EU program, very large one, called CD Links, where the key integrated modeling teams are participating to build the next generation model and come to grips with the so-called nexus issues. And we also have an internal project at IASA with the Global Environmental Facility at UNIDO, where we are building the next generation model of our integrated assessment framework to deal with the nexus issues, water, energy, food, in the context of urbanization and development. So I will spend a few minutes talking about the urbanization in my talk from the systems perspective. But let me also say that all of this, in some ways, I think is a moral issue. And I think that Pope Francis's encyclica raised lots of attention in New York and his presence in New York. And I think it's very, very symbolic how our attitudes in our society are changing, that we see the sustainable development as a moral necessity in order to live pleasantly on the planet and include everybody in the prosperity. So in the sense of the great Hungarian British economist, Lord Kaldor, the rest of my presentation will be a kind of stylized facts, relatively simple, and I would like to show you first this one. One way of thinking about this transformation is that we need to do more with less in the future. It's really in some ways ultimately about the efficiency, because the legitimacy of business as usual is eroding, and to achieve a vision of sustainable future, we need a real transformation. Some of the components of that are that we already have increased problem perception, and I think New York and Paris this month are symbolic of that, but also there are many actors of change, from civil society to governments. That is changing policy regimes, and I believe that it needs to change values and norms. So I think this is the huge task ahead of us and of the system science to provide the facts for how this transformation could be achieved. So in some sense, I would argue that we need a new social contract in the sense of the moral rules that govern relationship between people, and that needs to go in the direction of a vision of a sustainable future. I would argue for that, and I would like to give you one particular example of that. Carbon. I started with carbon. Let me return to carbon in the rest of my talk. This is how the global emissions looked like for the map of the world I've shown you to present, in time, as time series, and how they might look like in the future if we want to achieve stabilization at 2 degrees. My colleagues at YASA and the large community has been working very much with system models to understand that. The challenge is that the total carbon budget of the humanity is limited. It's an endowment that we all have to share, and it's limited for 2 degrees at roughly 3,000 billion tons. Now here's the problem. We have emitted already 2/3 of that, 2,000. There's 1,000 to go. So this curve, it looks so strange, not only because I don't know how to plot S-curves. I see Cesare there. We've been doing that for many decades. The reason is that, in fact, we would be over-emitting. It is very difficult to change the inertia of our systems to reduce the emissions as needed, so we would go over the target, and then we would need to remove some carbon from the atmosphere to so-called net negative emissions, technologies like sustainable biomass in conjunction with carbon capture and storage. So that's the challenge of us. So it's a technological challenge, it's a social challenge, but it's also a challenge of behaviors primarily, and this is why I'm thinking that the social contract is required. But not only that. I mean, we have to look at the people who are excluded. Let me show you some examples. Many of you might be familiar with the Lorentz curves. On horizontal scale, you see cumulative population, and on the vertical scale, cumulative consumption of something. So in a perfectly equitable society, along the diagonal, 50% of population would share about 50% of the common global good. Now, let's see how some of these things are distributed. The wealth of the world, very skewed. I mean, you can just see, and the bad news, it has gotten even worse in the last 15 years. We are becoming less and less equal in some sense. You could say that 80% of the global population has less than 5% of the total global capital. Another way of reading it is to say that 10% of the global population, the richest 10, control 90% of the capital. And so this is so fundamental for the transformation. It's a big inhibitor in many ways, that people don't have the means to develop. If we look at economic output, that has improved the distribution over the last 10 years, measured at market exchange rates. If you look at the PPP, purchasing power parity, it's a little bit more equitable and has also improved. And now here is an interesting thing, that if we look at some other indicators like electricity, it is distributed just about the same as GDP per capita. There are about 1.4 billion people who do not have access to electricity and have almost no economic power, live at less than $500 a year or so. If we look at some of the other indicators, here is a deep contradiction. Almost everybody has a phone, much more equitable. So 1.4 billion have a phone, they have no place to charge it, and pay 10 times as much as you all do for charging. So the development barriers are really fundamental and deep. Carbon is emitted the same way as electricity and GDP, not surprising. These are proxies for each other. And then let me just show you finally two more. Calories and water per capita, again, on the order of 1.4 or so billion people excluded. So we have to provide development for those people who will join the planet and stay within the planetary boundaries. That's the big challenge. And last but not least, let me go to the next part of my talk, which is the urbanization. You can see people, very few people live in the huge cities. Lots of people live in the small cities. I don't know if you have seen it. Notice that that's the yellow curve. So I would like to spend a few minutes on the topic of urbanization. And again, I think this is in the sense of what Simon said. Things should be made simple if we have a good theory for it, but not too simple, not too trivial. And Einstein also said, I'm a big fan of this statement, if you can't explain it simply, you don't understand it. Now, I'm not claiming I understand all of this, but at least I'll give you a relatively simple representation. So one of them is the rank size of the cities. Let's go to urbanization very quickly. 2,000 years ago, Rome had 1 million people. Baghdad, 1,000 years ago, reached again 1 million persons. It was the largest city, and you can see how the others are distributed. Then we had a number of cities, in particular in China, but also Constantinople, all in the range of about 1 million people. And then, in the midst of the Industrial Revolution, we achieved 10 million. And I'll try to give you reasons why that was possible, primarily because of the railways, replacing horse riding by railways. New York, 10 million. And if you look today, the distribution, as you can see, has been quite invariant. But it looks like we don't have enough big cities. That is actually not true. If we look at the organizational way how the cities function, the largest urban metropolitan areas, like the belt from Tokyo to Osaka, I call it Shinkansen, they have on the order of 80 million people today. So the structure has been quite invariant, and it's interesting if you look at US, there have been many studies at US, it's the same at most of the regions. We have quite a strong invariant structure, so it's a system property, and it has a lot to do with networks, I believe. Now, at the same time, from many of the studies, we know that cities are like gravity well. People are pouring into cities. We have 3.5 billion people, as you can see from this curve, living in the cities today. It'll be probably 6 to 7 billion during the rest of the century, in 50 years from now or so. So the cities will be doubling. Now, assuming that the structure will be invariant, that means that the largest area would be on the order of 150, maybe even 200 million. And for that, we would need completely new infrastructures. And cities are in some ways organic systems. And I think a good metaphor, and I think that fits with what Simon was talking about, if we look at the living cells and the cities, there are strong metaphors. The metabolism of the cities is open. That's our problem today. Cities account for about 80% of energy, 80% of emissions, but have only 50% of population and cover about 2% of the area. So the challenge for sustainable development for the urban areas, since they're growing, is how to close the metabolism, like a living cell does. The problem is that we, of course, don't have all that much data. That's the irony of the computer age. One of the few cities where we know what the inputs and outputs are relatively well is Brussels, and you see how open the system is. I'm not going to go into the details, but what comes in comes out in a more, at the higher level of entropy after it has been used by the city. But there are some other interesting characteristics of the cities I would like to also mention in this systems context. And that is, if we look at cumulative population of the number of cities for which we did manage for the Global Energy Assessment to assemble the data and look at the final energy used in those cities. Those of you who are mathematically minded, you will see that this is a power law curve. It actually scales across the cities. And the interesting thing is that the cities that are marked in red, are the ones that have energy consumption above the country average. And I think this is quite interesting because most of them are in the global south, and this is where most of the cities are growing. That means that the energy needs would be increasing, and this is why we need a huge transformation to allow for that. I see Louis Betancourt sitting in the first row, and he and Jeffrey West have done lots of scaling work on the cities. I will not go into it, but in some ways, this phenomena of how the cities structure is not that different from the galaxies in the universe or the words in the language and so on. This is just one illustration of it. But in context of that, I would like to add another thing. We only have 24 hours in a day. And that's relatively little time for all of the things we have to do, especially those of you who are all very, very busy. This is a caricature, of course, very, very simplified. But if you see in the middle, we spend in US about 66 minutes on household chores, 150 on watching TV. And this is what I wanted to highlight, about 50 minutes to an hour on commuting. And that's roughly true around the world. It's one of those stylized facts. People commute on the order of 1 hour a day. If they commute much more, they're not all that happy, or at least they're very sleepy. So let's connect those two things together. 1 hour travel budget, cities expanding, urbanization expanding, and mobility expanding. And this is a very unique data set from my colleague Arnulf Gruber that I wanted to share with you. It shows the mobility in France. Very difficult to do. For most of the countries, I think it would be a good master thesis, maybe even a PhD thesis to update that and look for other countries. So it grows at about 4% per year. And please note one thing. With the horses, one could cover on the right side of the scale about 100 meters a day. Railways in brown, about 2 or 3 kilometers a day. And the cars, about 50 kilometers a day. Now, 50 kilometers a day within 1 hour means that the cars are travel about 40 to 50 kilometers per hour on average. And that in some ways defines the size of the city today, and we will need the new infrastructure if the urbanization continues growing as it does today in order to make this sustainable transformation toward the future. Another effect I wanted to talk from the systems perspective is the fact that as the technologies diffuse, the costs go down. And this is another power law. I will show you here for the horses and the railways, the order of magnitude of improvement is on the order of from about 20 to 2 pence per passenger kilometer hour in UK. And there are many such phenomena. I of course have no time to go through the detail, but let me just show it to you in a stylized way. If we have an old technology, and there are usually many new ones are designed, but most of them are not successful, the one or two that really makes it can improve the cost significantly and disrupt the old technology. But that requires new behaviors, and that's one of the basic mechanisms, in my view, from the system perspective of achieving this transformation that would be ahead of us. So let me come slowly to the conclusion. How might this look like? This is one study for Asia, where the largest urban areas would be. We would need new infrastructures. This is perhaps where 200-300 million people will be living. As you know, these are all cities that are in the range of 20 to 40 million already today. We would need new infrastructures. One possibility is magnetic levitation trains to connect these huge urban areas within an hour. By the way, Japan has made a decision to build maglev from Tokyo to Nagoya first, and eventually it will go to the Osaka. And what you see in the insert is a kind of a supergrid with a transport and information system. The energy component would be hydrogen and conducting electricity. Maybe energy would be coming from the desert, or from the solar power plants and other sources of energy that would be more equally distributed around the area. So this is a big challenge. It's clear that we will need very big investments, and it will require fundamental changes in our systems. Let me just try to illustrate that briefly here. This is how energy reaches people. At the beginning of the Industrial Revolution, and for the 3 billion today excluded, it comes in form of solids, and that's a big problem in closed areas. About 4 million people die a year from that. Then came the oil age, the liquids, and the grids are now expanding, which is electricity primarily and also natural gas. And in the scenarios that achieve this transformation that I was talking about, the grids would play an important role, and that's why I showed you the picture of the infrastructure before. The grids would be expanding. This is common to most of the scenarios that achieve 2 degrees, that achieve universal access and economic development around the world. But from the system perspective, we have to look at other dimensions. For energy, you need water. I don't have the time to go into the details, but we have analyzed that. So other systems will be changing along. They're combined together in the network. So water used to go for solids, for mining and power plants. In the future, it will go toward generating hydrogen, building the renewable energy systems, nuclear where it's acceptable, and other zero energy carriers. So I would like to come now to the conclusion, because I've exhausted my time, and I would like to show you how some of what I started with, how some of the development goals could have huge synergies among them. This is based on the work of my colleagues at IASA. On the vertical scale, you have the global economic output. Today, it's about 108 trillion, and this is the percentages that one would need per year to achieve certain goals. One of them, important one, is energy security. If you read that, that translates then into 200 billion. Another one would be eliminating air pollution, and in particular indoor air pollution, on the order plus and minus 500 billion, and climate change, as you can see, it's in the order of 1,000 billion or 1 trillion. This is in our integrated assessment model if you pursue these goals separately. However, if we had integrative policies to do that simultaneously, avoiding the barriers among achieving those goals and working synergetically in the right direction, the total cost would be slightly higher than just doing climate. That means that the additional cost of achieving security and eliminating air pollution would be very minimal, or the other way around, since energy security and air pollution are important, if you stack those two together, we would get the climate goal for free. And my hope is that once we apply the best methods we have in modeling the 17 Sustainable Development Goals, that we will find lots of synergies, and we have to make sure we avoid huge barriers. Thank you.